Great, then welcome to the last talk. My name is Tim Heldmann. I work at the Scientific Computing Institute here at the TU Darmstadt, and my talk is named Gotchas for Clang-Tooling. And it was originally named Things That I Assumed Were True About C++ That Apparently Are Not, that I wish I would have known before starting with Clang-Tooling, that I now know that you might not know. And so I thank Jan-Patrick Lehr for inviting me to giving this talk and suggesting a much better title for the talk as well. So, what did I do? I wanted to generate call graphs, which means that I want to turn what you see here on the left to what you see on the right. If you have a function, you will get a node. If you have a call, you will get an edge. And if you have another function, you will get the node where the call is getting to. Why do I want to do this? I wanted to extract mini-apps. You can ask me how about that one later over pizza. And how do you want to do that? Well, in this case, you just go and ask Clang, because Clang knows. It's a compiler. It is able to treat all kinds of functions. And so you go ahead and ask function, hey, Clang, what function does main call? And Clang is like, Clang compilation failed, error, use of unidentified thing, foo. And I mean, I'm not that new to C++ because I know how front-end and parsing works. So what basically happens if we have this preprocessor that resolves all your macros, the Alexa hacks all the text into tokens, the parser tries to figure out if they make any syntactical sense at all, and then the semantic analysis is where all this matching happens. Which function is which function, which call corresponds to what, and we need to get to at least here, because the AST, as we just seen in the Clang tidy checks, is where most of the interesting information is encoded, and code generation is something for another day. So, what C++ 101 tells us, as soon as we encounter foo, the compiler does not know what foo is, so we need to forward declare the function foo so that the compiler at least knows, hey, there is this thing called foo. We do not need the definition, which is the thing between the curly brackets. We just need to tell the compiler this thing exists, treat it, and the compiler is very happy and says, okay, compiler return 0. So, what we now learned is Clang parses your source code top to bottom, and you can only use a function that is known before you can use it. And known means that the compiler has at least seen some kind of signature for this function. You do not need the definition. Great. This is something that is common knowledge for most people that have spent some time with C and C++. And so if you want to generate a call graph, what you do is if you find a declaration, you add the node. Then you find another declaration, you add another node. Oh, apparently this declaration is also a definition. You step inside the definition, you find your call. Wham, bam, Bob's your uncle. You got a call graph. Great, which means that we have Tim's theorem. Call graphs are very easy. In a valid C++ program, we should encounter a declaration for every function we see used, and call graphs are easy. Things done. Well, apparently not, because this works. If you encase the same code that we had before forward declaring the function inside a class, and you ask Clang, what function does main call? Clang is like, well, main obviously calls foo. Why shouldn't it? Because apparently you do not need to forward declare something as soon as you wrap a class around it. I mean, it's not something that I did not know. I mean, I have used it before. It's just something that I wasn't aware of when I tried to design my code to generate me some call graph. But I mean, what we now learned is it's basically non-member functions that work the way that we assumed. And if we have this special case for member function and classes, well, it still works out. What we just need to know is you do not need to predefine a function in a record. And if you want to generate a call graph, you can basically keep most of your logic. You just need to add this extra case. If you find a record, you need to add all the declaration as nodes to your call graph so you don't segfault out. So you find your declaration, you add foo, you find the class, you add everything inside the class. So once you step through your function 1, you can already add the edge to function 2, even though you haven't traversed the function 2 yet. Well, it's okay. And then in main, you can just reuse the same logic. Great. So we update our theorem. Call graphs are still pretty simple. We say, okay, this is only true for non-member function. And for classes, we have this exception where we only find the class beforehand, and we need to extract the functions manually. Great. So I went on my merry way, and I found this beautiful little thing, which we saw in the Clang tidy talk as well. It's called an immediately invoked lambda. And so you carefully ask Clang, uh-oh, this looks dangerous. Do you know what function main calls? And Clang is like, well, it obviously calls ZZ main4 enc3 $_0 CLEV. I mean, nice to meet you, ZZ4, but what? Yeah, it's called name mangling because the names you write inside your code are not what the compiler uses, because the compiler tries to generate a unique trademark identifier for every named entity. And why? Because C++ has something that's called overloading. It's not a problem if you work with C, it's only a problem if you work with C++. What is overloading? For the uninitiated, these functions have the same name, but they share different parameter lists. And so you need different names to actually figure out what's called. So you have this thing called mangling. And mangling is a great thing because there is actually a standard for it. It's the Itanium ABI that Clang follows. And it's great because you can look up these things and you figure out, well, that Z means this is a mangled thing. It has a 3-letter name. These 3 letters are foo. And V means, well, it had a parameter and it was the built-in void type. And this only differentiates in the I, so this thing had a parameter with a built-in integer type. Great! And the smart and astute among you will now figure out that this is basically all the information we had available to get from the mangled name back to the demangled name. Great! If we have z3 foo v, we can return foo void. Now if we have d3 foo I, we have foo int. Great! And if we have zz4 main, our lambda function, well, we obviously, what? We get zz4 main enc and just cut off everything that's past the dollar. Because mangled names containing dollars are non-portable and you do not care if they are demanglable, how to demangle them. You just say, well, this apparently is the name, deal with it. But I mean, it's not that big of a problem, right? We just can add this thing into our call graph and we should be fine, right? Lambdas are not a problem. Clang handles them, the mangled names, fully automatically. We do not need to do anything to support lambdas. It's an absolute miracle and we support lambdas. So you write your code, use the same logic, you add your edge main, and then your program segmentation falls and dumps a core, and you're not quite sure why. And then you start to look into how lambdas are designed, and we already heard how lambdas are designed. Lambdas are basically classes. But we dealt with classes, right? If we find a class, we extract all the member functions of the class, add them to our... Right? We had logic for that. Why doesn't this logic work? We tried so hard. Well, it apparently does not work, so we look into the module dump, and as you can see, this module dump for these 3 lines of C++ code generate 29 lines of module dump, so those get big very fast, so I cut them out to only include the most important parts. So we try to figure out what's going on. Well, we have some kind of operator call expression. Great, that's this one. What are we actually calling? Well, we reference some kind of declaration. Great, we reference the operator call of our CXX record decal. Okay, what is this? This is the method decal operator. Great. Which CXX record is this from? Why do we define our CXX record after we already called to it? How does this make any sense? Took me some time, and then in my desperation I asked in the LLVM Discord, great people with great answers. This does not work, lambdas are a problem, Clang does nothing fully automatically and miracles don't exist. So you get this answer, which basically means normal define and declare rules don't apply to the compiler. They are something dreamt up by language designers to force programmers to write vaguely sensible code. As long as the compiler has access to the record declaration, in this case the CXX record decal it can use, then the class is defined as far as the compiler is concerned. Well, great. Apparently traversal is not top to bottom because things are different now. Then we update our theorem and it starts to get ugly because in a valid C program we encounter every non-member function used except for classes where we find the class beforehand and need to extract the functions manually, except for lambdas which are classes but we do not find them beforehand because they are compiler generated. Great. Okay. Luckily, lambdas is the only compiler-generated piece of code inside C++, right? No, there are... Oh, wrong. Yeah, what we do now is if we find a lambda, we add the node to the graph and the college as well. Right, lambdas are the only compiler-generated thing. No, they are not. There is this thing called a template, which means you have this thing and you can call it with some different parameters, and apparently Clang treats them as normal functions. Wow, great. What functions are called by main? Well, those. And I mean, those look like familiar mangled names. They have this T for template and S0 is substitution. Wow, this apparently works. Great. So what we do now, we just throw a template in our tool, and the first thing we get is main. This already is a little bit weird because shouldn't we have, this is a function definition, right? There is code here. This should be generate a callback, and No, it does not. Segmentation fault. Well, great. So we try to look into that, and there are a multitude of different options that we can now explore. Is it because we have some kind of parsing problem, right? It could be because of those mangled names, because now we're dealing with like templates. It could be because of compiler-generated code, because templates are compiler-generated code. And I'd like to have a show of hands. Who thinks it's some kind of parsing problem? Oh, wow, great. Who thinks it's because of some mangled name issue? Okay, which means that I should see some hands because it's due to compiler-generated code. Okay, at least some hands. Okay, great. It's not because we have a parsing problem. We traverse templates beforehand. Everything is fine. And it's not because of mangled names, because template function mangled names just work like any other mangled name. And surprise, it's not because of compiler-generated code, because the compiler does not know more than we do, as was the case in the Lambda functions. But there is an asterisk here and here and here, because it's partly because of all of them. We do traverse the template before we use them, but we do not traverse the template instantiations before them. We need to do this separately. Template functions do have mangled names, but the original template description does not have a mangled name, and the compiler does not know more than we do. The compiler just refuses to mangle the name of a template description, because template descriptions are template descriptions and are not functions unless they are instantiated. So you need to deal with all of them above, which means that I don't want to do this anymore. We update our theorem again, which now means we have an exception for templates which are also compiler generated, but we do not find them beforehand because they are not classes, and we need to differentiate between the different instances of said templates manually, because we do not automatically traverse the declaration, and we cannot add the template description to the graph because the template description has no separated mangled name. And that's all, folks. So thank you for listening to me rambling on about Clang. And pizza is ready, I think. Oh, and those, by the way, are only the direct calls. There are different kinds of calls, but we are not, yeah. Yeah, sure. Constructors and destructors are member functions and should work TM. Yeah, okay. Yeah, there are okay. The same constructor can have multiple different names, and for this I referred to the very smart solution of a person that worked at this institute before I came here, who just had the idea to just generate every possible valid name for a given constructor and destructor and just add them all as potential call targets, which is not the best solution, but it's one that works very well and generates very little segmentation faults. And I have seen my fair share of them in the last half a year. But yeah, still not fully solved that problem, because it's also configuration and mangling schema dependent, so it gets very tricky very fast to do constructor and destructor mangling and identification correctly. Yeah, any other questions? I mean, it should have been recorded, so if you have any interest in listening, you can, it should be possible. There's still audio, great. Okay. Oh, one more question, yeah. I mean, template, yeah. As soon as you specialize it, it gets added as a sub-child of the template declaration, and you need to manually traverse the template declaration to find all the instantiations, but then you can just traverse them as normal function declarations, and this works quite good. I'm not quite sure about how partial specialization work. I think those are just another instance of a template declaration. Yeah, you could have partial template specializations. For classes, yeah. That's a good question. I think we traverse class templates the same as we do function template descriptions, and then treat it as a whole class, and then use the logic where we traverse the class body, extract all the member functions, and treat them as possible valid call targets with the adapted signature. because we are only interested in signature changes inside our call graphs, that you might have some template-dependent variable members inside your class is something that we are luckily not concerned with when generating call graphs. No, I luckily have not encountered one in the wild, but I should probably. Oh God. Okay, I see. Okay, then thank you again, and pizza time.